thing. Most of the discussions will be on BSc level things, except many places you will find astronomy related things. So like we will be discussing black body, but in context of astronomy. So these are the overall things that we will be covering. Mostly it will be beginning with telescopes. Then we will define, again, many things are primarily definitions. I will be talking about stellar magnitudes. Then we will go through black body radiation and how it, in the context of astrophysics. Then we will go into a little bit of instrumentation, images, photometers, and mostly tomorrow's, because I don't know, we might cover up to this point if at all today. Otherwise, tomorrow we will be continuing the same time on spectrometers. Then we will see how to connect a spectrometer and a telescope. And finally, spectroscopy, when we do what are spectral lines and spectrometer itself. And towards the end, we'll talk of how you go to an observatory and prepare yourself before taking an observation. So again, mostly these are not going into any depth, but in tomorrow's lecture, you will have the references related to all whatever I'm covering. And most of the things, all these books are there in the library, so you can have a look at them. And this particular whole lecture, it's a PDF. So after tomorrow, I will be sharing with the coordinator. So whoever wants should talk to coordinator if they want a copy. So many times you just take the copy and don't use it. Again, it's only important that you sit and attend. Otherwise, if you do it offline and see the PDF, that will not help. Because many things which I speak may not be already in the talk material. So that's why Blackboard also will come on and off. So firstly, I will tell you what a telescope is. Since this is an introductory astronomy and the summer school together, the question is, how many of you have actually used a telescope? Just raise your hand. What size typically? Size of the telescope? Loud, I can't. 8 inch. 8 inch, I see. And binocular, I'm sure everybody has used binocular, right? In fact, in our school days, we actually used to make a monocular. I will talk about that. So telescope is a very much in thing now. We will go in details what the telescopes are, little bit of history, which may not cover here, but you know the telescope was first actually invented by Galileo almost 400 years back. And in 2008, I think it was the 400 years of telescope when there was a big event in astronomy all over the world, including India. Many people don't know that 2008 was also 200 years of Darwin, not, of course, astronomy. And the telescope by name was not known before Galileo, but it was always what you call known as a spectacle. The lenses were there. And also, just a side thing, that during 2008 event in Bangalore, the students during, I think it was ASI meeting, students organized an excellent play, a drama, on how Galileo in the last 10-20 years of his life was suffering because he was in Italy, and that time the religion, Christian religion, was so strong that whatever the Christian religious people, popes used to tell, the public had to agree. So only Galileo discovery or invention put them into the real perspective of actually seeing. Galileo was the one who actually saw the 4 moons of Jupiter, they are moving around. So some of you, when you go back, when you do these experiments, if you have an astro course, you should insist to see the moons of Jupiter in the night. Sometimes all the 4 moons will be clean, one of them will be going back. So it's a very interesting observation. Of course, Saturn rings are also a good thing. So in that play, it was, the saddest part was towards the end of his life, his daughter was with him in the jail. It was actually, he was on bedridden. So that play was actually enacted by the students of the Bangalore Institute. So it was very sad part of his life that he was recognized much later after his death on this telescope, which was a major discovery. So there are two basic types. One is refractor using lenses and reflector. We will cover both of them. And the main part of the telescope, the front part, which is the main kit lens, or in binocular, the front lens, or in mirror base, the big mirror, is called the objective because that is the one which collects the light. And it also tells the type of material, whether it is mirror or what type of telescope it is. So a refractor usually has a glass lens. The largest refractor can be even 5 meters. We'll see a picture of that. The difficulty with lenses is that it becomes too heavy, the glass material, and balancing the telescope. Also, making a glass lens of large size. Why large? Because you have to collect more photons, 1 by r squared. So more the area, more light can be collected. So you have to go fainter. So everything is getting compromised. You have to go fainter, you have to collect more light, and you have to go bigger. So, but lenses, making a large lens is always difficult because polishing effects, then there are air bubbles, etc. We will see the disadvantages of refractive. So very soon, almost 100 years back, people realized that we have to go for mirrors, and we will see the advantage. So this picture only shows the two things. The top one is a refractor lens. This is the objective lens, as I said, and here this is the primary mirror, which becomes the objective. And you see the light from stars, which is usually from infinity, will come and get focused here somewhere, and the beam diverges, and you have an eyepiece. Whereas here, what happens? This is a much more compact design. This is only to show in the same scale, although the telescopes can be very compact. The thing is, you have to hold this light here and take it out from here. Which means now you see the major difference is this is a lens, so there are two surfaces. So light has to pass through two surfaces, which means each surface it is losing some light. And I may or may not get a chance to tell later during the two talks. Each surface the light hits, the absorption loses 4% of the light. So 2 means 4% into 4%. So 0.4, 0.04 into 0.04, you can calculate. You're continuously losing the light. Here, there is no refraction, it is reflection. So there is no light loss. There are other problems. This is also a mirror. Here, of course, these are common. The eyepieces, they are small. The light losses are there, but people try to do the coating. See, nowadays, my spectacle or people who have seen, they look bluish. The trick is they do an anti-reflection coating. It's any spectacle shop, you tell you want anti-reflection, they will do. And why it looks bluish? Because it's a trick where the optical band from 4,000 to 7,000 angstroms, the part which is visible to us, which is a very small part, we will see somewhere, is the yellow-green region. That part, they reduce that 4% per surface to 1%. So it's a big advantage. But the energy is distributed in the other bands. So for human eye, it's okay, you are improving from 4% to 1%, but the other band is loses. Okay, so that's why it looks bluish. I mean, this kind of small things I may keep telling you, which are your general day-to-day effects, but you should know. So this is the general situation where you have a lens or a mirror, and you focus it either a human eye or a detector. Of course, human eye was used for several hundreds of years when the actual detectors came only 100 years back. So we will see those things. So this is, I was mentioning, this is the Lick Observatory in US, Western US, where this person is standing here. This is a large telescope. There's a big lens here. And it's all up close. There is a dome, of course, which will open. And it's a very old telescope, but still it is used today for a different reason. Even though you have mirrors and other things, it has one big advantage. Firstly, you will see that it's a closed tube, so there is no dust entered. And once you align these two lenses, they normally don't go out of alignment. So it's a very useful technique. And today they are mostly used because, see, although there are light losses, they have done anti-reflection and all that. 100 years back there was no anti-reflection, but they have improved those things. But you're still losing light here compared to mirror. But the bigger advantage is in one go, if you are taking a picture of sky, where there are many objects, galaxies, in one go you can take the image. And then you can go particularly to those particular objects and take spectra. So we will see how the modern things, they don't use the full lens, they use actually a grating. So each star becomes a spectrum. So these are the advantages. They are very rugged, as I said, because there is no dust coming in, and it's all sealed. So also the air currents, which will become very important as we go along. Inside the dome also, if you open in the evening to compensate the outside temperature and inside, which can be hot in the day, all these turbulences are settled down. But in this tube, since this closed, there is nothing that is already sealed. Whereas in the reflecting telescope, it's an open structure. What you would have used the small telescopes are tubes, but usually the larger telescope, you will see some pictures, they are open structure. So the air has to be normalized with outside, which is not a requirement here. The major disadvantage is, firstly, is the color aberration. Now, this is something which I was studying in school time. Even we used to make this, buy some cheap lenses and make a binocular as a school project. But you will see these color rings because the refraction is function of wavelength. So you will see, suppose there is the parallel light coming. You can see the red light getting focused on this side is the optical axis and blue here. And if you look from this side, it all looks like rings. That is the major disadvantage called color aberration. So only way is to make it either a parallel, it is a planar convex lens to reduce this. But otherwise, this defect is something which is inherent in these telescopes. So that's what I have said here. They can be reduced with different optics. Other important thing is the glass itself doesn't allow ultraviolet to pass. So people who don't have specs are that way much safer because any thickness beyond some, for example, 1 mm or something, the ultraviolet which is harmful is stopped. Of course, you can do a coating and all that, but still, glass is good for that. But when you want to do ultraviolet observations, because optical astronomy in Galileo's time was only to the optical band, but now you go to the library, any astronomy library, including IUCAA, each band, X-ray, and people will be covering these. I will be talking mostly on optical and a little bit of infrared. So other bands, experimental physics in the labs have developed the detectors for different bands, and that has been taken up by the astronomers. So you can actually find a book, X-ray astronomy, ultraviolet astronomy. Each band there are enormous research and text available. So also, as the lens thickness increases, obviously the absorption in the glass goes up. So this is a problem. So all these things, and again polishing, perfect curvature. These are issues which are very difficult when you are collecting a big lens for glass. And again, the lens itself becomes extremely heavy. So very soon people went for reflected telescopes about 100 years back. And the basic principle is the light comes and gets reflected. This can be usually a concave or a parabolite, depending on modern optics, the different designs are available. But essentially the purpose of this is to focus it. Can be focused here, but then you can't sit here, right? And this, you would say this has slight obstruction, but actually this mirror itself is large and that obstruction is very small. So of course it's a compromise, but it's a good compromise compared to the lens. So they do not suffer from chromatic aberration, as I said. The mirror can be as large. In fact, I want me to need a separate top or somebody might cover. The telescopes, usually the single mirror can be up to 8 meters. And the modern telescopes, the one in Keck, has 10 meters, but there are many 1 meter hexagons. And the large mirror, which India is going for 30 meters, is a 30-meter diameter, but not a single mirror. There are 501 meter. And the ELT, the European one, is about 1,000 such mirrors. And that is about 45 meter diameter effective, but it will come down because many countries do. These kind of projects require huge contribution, but some have actually dropped off. So Indian thing is, with India, we are collaborating with China and Japan. and of course Caltech and some other countries. So they are all coming up together, and 30 meter means the diameter is 30 meters. Enormous amount of light you are able to collect. And they are cheaper, of course, because all you have to make sure that only one surface is very well polished. The other side need not, because that's closed. So the difficulty is the alignment can change. So usually modern techniques allow these things, but still almost every few days we have to check whether the star is focused and it is aligned. If it is not aligned, the star will not look round, it will have a coma. And since it is open, dust is collecting. So you have to keep cleaning the main surface, which is not easy, but there are techniques of doing it. And the mirror is coated mostly with aluminum. And aluminum with oxygen reacts and forms aluminum oxide, so it slowly deteriorates. The reflectivity starts from 91, 92% and it comes down, apart from dust deposition. So it needs to be recoated at least once a year. It's just another picture, but I will skip this. So as I said, this is the secondary, which is hanging on this. This is called spider. Three beams like this. And other ways to actually take the light out from the back. So this is not that. So this is the one, you see. The light is taken out from back. And here you can put an eyepiece, of course, but you can put heavier instruments. In fact, the modern technology allows an optical fiber to go from here all the way to very next room where big instruments can be there. But optical fiber, again, will have a loss of about 80%, right, loss. But you don't have to then balance with a heavy instrument. And typically optical fibers are there in optical as well as in infrared and so on. And that's a new technique. Okay, I will just sidetrack a bit. Most of this display, which you see, is something known to you right nowadays, even from school level. It's very important if you are doing anything in physics, or any experiment, not just astronomy. And the best book for that is Schramm series and other statistics books. But why I'm displaying, because many people are not aware, and I'm sure most of you are MSc background or starting at PhDs. This will be useful for everyone. Very simple concept, but towards the bottom is the important thing which in the research you see what is 1 sigma and 3 sigma. So that this only is a slide, and the next one which clarifies your mind. You can never do mistakes there. So for example, mean is of course simple. If all of you sitting here have different heights, take a mean, and suppose the number is 15, I divide by 15, I will get the mean height, okay, which can be, let's say, 5.5 feet. And then the deviation, each one of you, how much you deviate from that mean number, and then mean deviation. So all these are mathematically expressed there, and all this can be actually easily programmed in. Nowadays in Python, but it could be in any language, Fortran. Finally, you get the sigma, which is the standard deviation. And that can be, of course, plus and minus. And the next picture, this 68, 96, and 99 gets clearer here. And here you see, I will just try to explain on this. So you see, the outermost line is plus minus 3 sigma. This is just a scatter plot. You can do it on your computer. Just take some data. There are about, I think, few hundred data points. There are two scales, X and Y axis. And of course, all of them are not ideally on the straight best fit line. And best fit line need not be exactly a diagonal, by the way. And so there is a correlation coefficient coming out from this. But more importantly, the plus minus 1 sigma is the inside 2 bars. So those 3 points which are totally outside are outside 3 sigma. Okay. So ideally, if you go up to 3 sigma, most of the data points are covered in experimental observation. In this case, of course, there are outliers. So they are also called outliers. But within plus minus 1 sigma, only 68% of the data is there. and within plus minus 3 sigma, 99%. This is about 100 data points. So this is something which is just basic statistics which you should know. So let's move now. This is the first definition of magnitude. So again, I should tell you that astronomy is a very old subject, not just Galileo 400 years, but even otherwise 100, 150 years old. And many concepts are basically on the visual observation. The detectors were not there 100 years ago. So what happens is everything was scaled to our human eyes. And human eye, you know, just like our hearing, is a log scale, right? You have decibels in audio. Similarly, here it's a log scale. So if you see this horizontal line, 0 is at the center. Now, when I say 0 magnitude, the Vega, the star which is in Lyra constellation, I don't know whether somebody will be covering the time and coordinate system, but there are some books which give my references, you can see. So Vega is not available right now. It will be available in the second part of the year. So that's a star which is 0 magnitude. And everything else on the right side, which is plus, is faint. And this is a log scale, remember, just because human eye was used. Today, if you have CCDs in your cell phone or more sensitive detectors, then they are linear devices. Okay, but if CCDs were there 100 years back, probably people would not have done this log scale business. But in a way, it's good because why human eye has this logarithmic? Because this is a room you go directly in the sunlight outside, enormous difference in the light shadow. In fact, that's a common question I ask to audience. So suppose this room, I switch off all the lights and just a small light is on, and your eyes are used to it, right? You will usually get used to the darkness. But then you're asked to go outside in the bright sunlight. How much is the typical light level difference can anybody tell? Suppose inside it is 10 photons. Whether outside it is 100 photons or 1000, just a number you can guess and tell me. You can be wrong, but you tell me. I just want you to gauge the difference, that's why. How much will be the difference for sunlight? 1000. Anybody wants to improve on that? 1000 is wrong. Loud. He is kind of closer. So it's almost 10 to the power 6. So imagine the human eye, just because it is log scale, it can adjust this kind of difference. It's a million times. So it's enormous, is the nature which has provided. And of course, because of that, all these definitions came. I have written there faintest naked eye star. Now that is seen not in a Pune kind of sky or any city. You have to go to very dark place, no moon that night. You will probably be able to see up to +6. That's a normal eye. People who have specs will not be happy to do that. And then fainter and fainter, the most faintest objects can be observed up to +25. This is a log scale. And that kind of faintness are the arms of galaxies and so on, which are almost merging into the sky. The sky brightness typically in a very dark place will be +19, +20, very dark place. And on the other side, you have sun, which is sitting on the other side, which is -26. Of course, sun is a very bright star, and very soon we will see when we define the actual magnitudes, the actual value. All this is mess because this is all related. What you are sitting in the night and seeing. So the moon of course have phases. Venus also, because Venus is not Venus, but the inner planets will have phases. And the brightest the Venus can become even -4. Okay, so this is just the apparent magnitude. This is not the real magnitude because there is no distance we have not talked yet. And remember, astronomy is a subject where distances itself can be so large. The way we will measure the distance is the very first level. You can go to cosmological distances as well, which I will not cover. But yes, distances can be megaparsecs and huge distances. So this is how the magnitude is defined. M1 minus M2, 5, which means the difference between two stars, if it is 5, then that is delta M. And the flux ratio, the actual counts, our eyes don't have a way to measure counts, but the detectors came later and they could count them, is a difference of 100. And that table talks you, if there are two equally bright stars, then the fluxes are exactly the same. And that's why M1 minus M2, 2.5 log 10. Remember, it is a log 10, F2 by F1. Or you reverse it, F2 by F1, 10 to the power 4, M1 minus M2. So this is a very useful formula, and everything is relative, of course, right? So unless you know M1, you won't know what is M2. That's why the real astronomy problem, because everything is relative science. The only way is to quantify some of these things. So now, I already told you, V stands for the visible band. We will soon see what is visible infrared and so on. So visible band is very limited. In the visible, by definition, what human eye is tuned to. And sun is minus 26, Sirius, the brightest star, is minus 1.44. And that's a crude formula, limit, and subscript is B. So if a kid asks, use your telescope, 8-inch or whatever, somebody said 8-inch, you put the D there, diameter in millimeter, okay? And that is the limit that telescope can observe. Assuming, of course, you are using human eye, okay? And again, this is not a very accurate, because there is many things, absorption, etc. not involved. So limit of for human eye, the D is small, because our human eye, I talked about the dark room, the human eye the pupil can become as big as 5 or even up to 8 mm. So if you put in those numbers, because in the dark adapted sky, the pupil will be very large because they are trying to naturally accept more and more photons. So 6.5, 6-inch telescope diameter will be 12. You see, it is not going, it's still a kind of a law of relation. Just because 6-inch becomes 3 times 18 inch doesn't mean you can go 3 times better. It's a log scale. So now we are slowly reducing the distance. Now, this picture is very clear. Earth in June, January and July, 6 months apart. And that small angle, there is a star there, whose distance you want to know. Again, it is relativity. The background star are further away. You are trying to measure a star which is closer to close. And that small angle, 6 months apart, you can measure with some accuracy. And it's a trigonometry then. It's a small angle, so tan theta is theta and so on. And by the basic concept, you can get the distance. Again, remember that smaller the angle, further away it is. But there is a limitation. And this is called trigonometric parallax method. This angle is called parallax angle. So, if that angle is 1 arc second means 1 by 3600th of a degree. Very small angle. That distance, so if this angle is 1 arc second, this distance, this perpendicular if you draw, is 1 parsec. It's a definition, parsec. If the angle becomes half, obviously the distance is becoming longer, so it becomes 2 parsec, and so on. In fact, surprisingly, all the stars which you see, not sun, although sun is a star, they have this angle much smaller than 1 arc second. Even the nearest star, which is Alpha Centauri, is 4.3 light years, which is 1.3 parsec. And that's the nearest one. All others are near outside. The corresponding angle is 0.758 and is 4.3 light years, because that much time it takes for the light from that star to come to our solar system. Earth and solar system at these distances are same. For sun, it is 8 minutes. So at the last line, you have 10 parsec is that angle is 0.1 and so on. And is directly about 10 to the power 13 kilometers. Remember, the best way you can measure in this trigonometric parallax method is 100 parsec, which is about 0.01 arc second. Beyond that, the instruments are not accurate enough. Then, of course, you have to do spectroscopy. Then you have something called spectroscopic parallax method. Then you have cosmological distance. So again, there are different techniques evolved over the years. Now, this is a very nice picture. On the left one is what you actually see. I'm sure in the night, Sirius is now almost setting, but you can see them. And you can see the Sirius there. And it looks, the bigger circle means is the bright star. And Sirius is, of course, the brightest star. And you can see all the other stars are there. But actually, if you bring all these stars to a fixed distance, because somebody had to come out with an idea that you have to measure the distances. So astronomers thought, let us say, now I defined parsec, so 10 parsec. Let's say we are sitting here on Earth, and there is a hypothetical plastic sphere, which is 10 parsec from the distance to the radius of that sphere is 10 parsec. And for a moment, think all the stars which you see in the night come to that surface of that plastic sphere. So that's how it will look now. So now, once I have told that, let me call 10 parsec as a standard distance, the magnitude now measured on the right side, all the diameter corresponding to those magnitudes, will be the actual, or what you call the real magnitudes, absolute number. This is just a picture to show you what is happening there for that moment. And this is the explanation that the standard distance is 10 parsec. So suppose a star is at 40 parsec. 4 times the 10 parsec, it brought to that 10 parsec, whatever star it is. 4 times closer, 1 by r square. So it has become, it's a log scale, so 16 times brighter, which means 3 magnitude brighter. So a star with small nv as +9, it's a faint star at 40 parsec. Hypothetically, it has been brought to 10 parsec, it becomes +6. 3 magnitude brighter in the plus scale. So I can now designate as a capital M for that star, which is the absolute. So the magnitude apparent is +9, and the real is +6 for this star. Now this is only definition, and this is how this table talks about those things. So now you see, Sun is actually not a bright star at all. It's just because it's close to us, you think it is bright. It's only, in fact, it's a faint star. It is +5 on that scale. Sirius also, although it looks so bright, it is +1, 1.5. Ranjan, the star, which is a blue star, what is blue and other colors we will talk when we do spectroscopy. It's actually a bright star. It's -7, quite bright. Then Betelgeuse, the red giant, +4, and it's also -6. It's a bright. And I told you about Vega. Luckily, Vega, and that's why people decided, Vega is sitting at that 10 parsec position. So if you observe Vega, I have an instrument and I observe and I get 56 counts. One of you observe and get 66 counts. Now we too can calibrate our instruments because using the same standard star, which is actually a standard star. So every observation is standardized to Vega observation. Okay, there are other standards also because, as I said, Vega is not available all through the year. So we have other stars which have been standardized. So this is only, and at the bottom you see the distance modulus. So capital M minus M and pi is the parallax angle, or even simpler terms is small m minus capital M, then small d is the distance in parsec. So suppose once you have defined Vega and compared to Vega, you observe any other star. In principle, you do that small m minus capital M for that star, you can get the distance to the star. Limited to 100 parsecs, remember. So this is as a limitation. It's not a strict tool for much further out stars. Again, going back to telescope ability. So what does the telescope do? A distant object like that door, the frame of the door comes to me at some angle. If I use a binocular or a telescope, I will see finer details of the door lock and the handle and so on. So the angle, the field of view is reducing with a telescope. I am seeing finer parts of the same object. So that's why there is a limit how small you can see. And that limit, this person, he was called Lord Rayleigh, was a British astronomer, gave this R there in part second is 1.22 lambda by D, and that number is an interesting number, 206, 265. It's not difficult to remember. It is how many R seconds you have in one full degree. So, it's in a radian. And 360 degrees is 2 pi radians. So 1 radian, which is also a measure of angle, and you will know in your calculators, our times calculator just started. Before that, there were no calculators. So in calculator, when you do tan theta, tan 29 by 30 or whatever, that you have to take the option of degree or radian. So radian will come directly Calculator is doing internally with the chip as the program, but otherwise you have to make sure that you do it in radians. Otherwise, you will not get the correct answer. So 206265 is that many arc seconds in 1 radian. Okay, and so R 1.22 is a factor, lambda r is the wavelength, which means it also depends on the wavelength. So the smallest angle for a particular size of telescope, which you can see, is defined by this. So you can see that bottom I have given the examples, assuming human eye is a telescope. So very sharp, now again it's not arc second, remember, there is 1 arc minute, so it's 60 times less accurate, bigger angle. Very comfortable vision also is 4 arc. So the thing about Rayleigh will appear many other places also. So this was defined, and very soon we will see the importance of this. Going a bit slow today. So this is the first time that you see this criterion. There are 2 stars, and purposely they are looking hazy because the actual star is not that sharp because of the atmosphere. So they are continuously moving. So that movement of the star, which is called twinkling in your nursery rhymes, it's not at the same point. It's continuously moving in the night. Every 10 milliseconds it is moving roughly. And that patch, each of them is about, in a very good place, is about 1 arc second of better. Remembering. So now, if 2 stars are equally bright, firstly, there is something called airy pattern. So you see this wave kind of thing. As for perfect sky, there is no scattering and absorption. So he defined both the stars are equal intensity, provided the cross section is sitting there, and the minima of the first fellow is at the maximum of the other one. Okay, which means here and here. So this was the definition. But this is only saying that if they are 2 equal sprightly stars, you can see them as resolved 1.2 lambda by t by this definition. But that doesn't mean if this star is very faint, I may not see this, I may see a small kink on one of the wings, depending on which side it is. That is also a detection. In fact, I should also tell you, this is also important, all of you have seen stars in the night, I'm sure. Most of the stars, 60% of the stars which you see, I'm not talking of planets now, are actually double stars. In fact, many of them are even triple. And this is the limit of the way the telescopes instruments are. As bigger and bigger telescopes are being made, people are finding more and more double stars and triple stars. So this number 60 is also old. Now, huge number of stars are, and many times they have a planet moving around and all kinds of things, and all this exoplanet business, somebody will probably cover. It's a very big thing in astronomy. In fact, all this money going into the large telescopes is the prime money is coming because we are looking for exoplanets. So let's not dwell on that too much. So this is again the same thing, that small angle. Let's skip. This is what I was saying, the airy pattern. So this is how the ideal star will look, but you don't see these outer rings because of the twinkling. Okay, this is an important slide. The telescope size on the left side is 50 millimeter, which is 2 inch, your binocular. 100 is 4 inch, 100 millimeter, and then beyond. But I have drawn a horizontal line there. Why? So what happens is, beyond that, if you make the telescope diameter bigger and bigger, you are collecting more light, but the atmosphere is not able to resolve that small angle. The right side is the angle which you are seeing. I was telling you the field of view, the angle on that door. It is continuously reducing, of course, 1.2 lambda by. So you can see that when you make it 10 times larger, 50 becomes 500, means half a meter telescope. The angle will become 0.23, but that horizontal line stops you from resolving that sharp image because the atmosphere is turbulent. It doesn't allow you to. So you will say, then why do I make larger and larger telescope? Because the atmosphere is anyway killing me and I can't see fine things. But remember, that part I will tell you later, but you are still able to go fainter and fainter. You go to space, there is no atmosphere, all these things will not be there. You make bigger and bigger, you go smaller and smaller. But of course, in space, you can't launch very telescope. Even the James Webb, which is after Hubble, the 6-meter telescope. It has multiple mirrors. Hubble was a single mirror. And even that, of course, is a fantastic technology. It's sitting at a place where no human can go outside. L1 point in the Earth Moon system. But why it is important? Because it's the largest telescope in space which has come. There is no atmosphere there. But so if you do this calculation for 6 meters, you can take it as a homework and find out how small you can see. There is no atmosphere, you can see it. But that is the limit of collecting the light, because bigger than that, today's technology, you have to come out of Earth's gravity. And it's not a single country spending it, it's a multiple country effort. So, and it took 10, 15 years of planning to win this. So that's why you will say that ground, why am I making 30 meter, 40 meter telescope? The trick is basically to remove that horizontal. I am telling in a school level, actually what is happening, this turbulence, to a great extent, it's a nature which you can't do anything, but there is a way, a trick to do that, because the turbulence, I will need a full lecture for that, but somebody will cover for me. Everybody has seen a swimming pool, if not knowing swimming. It has waves, and the bottom there are tiles. So if the waves of the thing, other tiles are not sharp, okay, because of this turbulence. For a moment, if everything is still, you will see very sharp tiles. Imagine the same thing, you are now underwater swimming and seeing the sky above. Firstly, your refractive index is cool. It's a higher refractive index, so the angle is reduced. Sine by sine out. But because of the turbulence on the level of the swimming pool, you are not seeing clearly. If people have tried water swimming, you can check this. Same thing, if it is very stable, you start seeing clear. Exactly the same thing the atmosphere is doing. But now, since there are multiple mirrors, and each mirror, the shape can be changed. You will say it's a glass, if I change the shape, it will break. But no, we are talking of optics here. The shape change is out of microns and extrons. So there are pistons which are moving this. It requires a full different, but I can tell you a nice book on active or reactive oxygen that I very can read it as a novel. It's very nice new technology, which came from actually your samples. So they are managing to measure the turbulence of the atmosphere by throwing a laser. Wherever you're observing, I'm putting a laser also. So if this is an optical, this is an infrared, so there is no difference. They form an artificial blob. I won't say a star, but at 90 kilometer altitude, there is a sodium layer. So it's a sodium blob. For 90 kilometers, it is almost not infinity, but it's far. And the same light comes back to the same turbulence. So now you have a way to check how the turbulence is changing. You have a way to modify the mirror shapes. These two together with a high-speed computer, if you manage, it is like you are actually not having atmosphere. It's called active adaptive optics. And most of the big telescopes, minimum will have active mirror. And adaptive is expensive and different ways of adaptive optics. Combine any telescope which is today more than 4 or 5 meters will have active adaptive. And the thing is so good, I have not seen an optical telescope in the night, but in the daytime, everybody has seen they project sun during eclipse, right? You see the sun eclipse. The sun is simmering like this because of atmosphere, because of the turbulence. But I have seen in La Palma, in Atlantic, they have a solar telescope, and there is a switch here. The whole thing, sun, it's a normal day, sun is observed with a huge screen like this, and it's continuously simmering. Okay, they are focused, some spots are seen. But as soon as they switch on that, the whole thing becomes lost. It's amazing how this thing, of course, this technology has developed over 10, 20 years. But today, so now the way Americans say that now when Hubble was there, you are matching with the big brother in the sky. So Hubble, there is no atmosphere, it sees a galaxy and all that, right? Very sharp image. Now if I'm doing this, switching on the adaptive optics, I can see much, exactly almost like that. In fact, even fainter because I can collect more photons. So let's move on a bit faster. I mentioned telescope has two advantages. One is mainly the magnification. I told you, smaller the field. This you can read it later, I will skip a little fast. What is the minimum focal length of the objective, the primary mirror versus your eyepiece? A simple ratio. And light gathering power, LGP, bigger the one on the yard square, it will collect more and more. So this is an example here, human eye, 8 millimeter I said, dark adaptive sky, versus a 4-inch telescope, NMM. So what is the light gathering power? 156 times more by using the telescope. And you can already see, you converted it into log scale, how much fainter stars you can see by your 4-inch telescope. We are almost coming to the end of the telescope description. This is the same number, 57 point this is the that many in 1 radian. And so that many arc seconds, that's the degree, this is arc seconds. Now, why I'm saying this, people have used 8-inch telescope, remember, and now very soon that is going because your mobile cameras don't have this number, but the cameras used to be written f by something. Okay. Now, in case of telescope, it is f by 11 means the denominator 11 means the focal length of that telescope versus its light collecting area is 11 times. So, the 8-inch telescope which somebody has used would have been a f11 telescope. And this is interesting. Sun and moon, this is only coincidental. If you are sitting on Venus and see Venus on moon and sun, they may be totally different. It's just coincident that on Earth, the angles separated by sun and moon are almost half a degree. It's only a coincidence. So you put in those things. This exercise is, suppose you want to take an eclipse picture or take a lunar eclipse also, which is easier because you are not seeing the sun. In your mobile camera also there is a field in which you have to, but older cameras were 35. So you will have to do this calculation. What will be the size of that image? You don't want it to overflow. At the same time, you don't want it to look like a very small dot. So it would come 18.8 by using this image. So this whole thing is called plate scale. Why it is called plate scale? About 40, 50 years back, even when we were students, photographic film was there. The film was the size of the computer screen, about 1 by 1 foot. So the image had to be focused on that film. So one had to know these calculations that how much will be the size of the object. It's a galaxy, the moon, sun, which you are imaging. So there are two ways of using telescope. Imaging is more critical because if you have to take an image, the edges also has to be sharp, which means the optics has to be very good. For photometer, it is not so important. It has to be focused, of course, but ultimately you are collecting all the light on one part. So it's not that important. But yes, the optics plays a crucial role. What quality of optics and edges have to be sharp. So today I'm supposed to talk up to 12:15, essentially. So remaining time I will spend on this. By the way, you can stop me anytime in between. Don't have to hesitate because these basic things I don't think others will be covering. Again, for example, blackbody, everybody knows, even from BSc level, what is blackbody. In fact, when the MSc students come for Viva last week, we had the exam. They were stuck at these trivial things, and we told them don't prepare anything beyond this. We are not, although they are astro special paper, we are not astrophysics. Basic condensed matter, detector, this is what they should know. I mean, the bright students will, of course, speak out very fast, then we move deeper. So, blackbody is an ideal object. In fact, just to tell you, there is nothing like a real blackbody, okay, which is defined as 100% absorption and energy. There are some standard blackbodies which are level 1 or even say level 0 of this theoretical blackbody in USA, where they have kept those standards. These are essentially made out of a cone of a steel, and they are black painted, and outside is also black painted, and there is a heater wire. And they do try to calibrate with the theoretical. But the radiation again is made with a detector. Detector is not 100% same at all. So it's also a real detector, it's not a ideal detector. So there are these factors which they incorporate, they call it as a primary blackbody. So usually if you buy a blackbody from a manufacturer, he would have calibrated against that primary blackbody, which is again not the ideal one. So this is the definition. And the Planck's law, everybody knows, is the blackbody radiation law. And it has special cases of Wien's displacement law and Boltzmann law. Again, I will be now talking of relation with star, and we are using only MK system. So this is a typical blackbody curve. I have purposely put the colors here, which is the visible by the 7 infrared, this I have drawn it. The biggest one is 6,000 degrees. Okay, so that is almost like sun. And you will see the sun has the peak also in that band, visible band. And that's why human eye got used to from our birth to the light, not to this kind of light. A quick example I will just tell you on that real life thing. But before that, let me describe this. So three things happen when the black body radiation changes its temperature. This is like a very cool star. These are hotter and hotter. And there are hotter stars which have peaks this side. Okay. And colors are seen. And this is the point which is going like this. So three things are happening. As it becomes hotter, the peak shifts towards blue. The area under the curve, which is actually the Stephen Boltzmann law, the total energy increases. And of course, the shape of the curve, of course, is there. So these are the basics of black body radiation. Now, before I move, I'll just quickly tell you why the visible band, being an old concept, called as, it could have been easily called as yellow-green color or something. But why not? Because human eye was adapted to sunlight. You will know during the cloudy weather, everything looks grayish because there is no sun directly. So all wavelengths are equally scattered. And that scattering effect is here what is happening. Everybody knows what is Rayleigh scattering, 1 by lambda 4. That's why the sky looks blue. Okay, 1 by lambda 4. But in case of gray, during a foggy or a totally overcast sky, it is 1 by lambda. All the wavelengths are almost equally scattered. But the quick thing which I should tell you now, this may be surprising to the boys and girls also. Human eye, 60% of the men are colorblind. This you may or may not. Color blindness itself has different levels. For example, I am a spectroscopy, but I am colorblind. But it has different problems. Like if there is a low intensity, I will have difficulty in distinguishing yellow and green, low intensity illumination. Girls particularly usually are not colorblind, but it's not true. You can check yourself now. Earlier you have to go to doctor, but now on computer you can as well check which level of colorblindness you have. In fact, my daughter, I didn't know that she was colorblind. She was also at a level. But girls not being colorblind is not so rare. You can check that. So why I came to this light from outside, you people have gone to a cloth store. You have always seen inside there are tube lights nowadays, you have LED tube lights and all that. Any cloth you are buying, you will always come out and check the color. Because your eye is used to that color, right? Not this color. Not only that, this is again something which you can check. Now, mercury lights are almost going because they are expensive, they are polluting the night sky. Because mercury has a continuous line over which you have a continuous band over which you have the mercury lines. You have done your basic experiments, the mercury green line and others. Whereas sodium has only two lines, B1 and B2, 5890, 5896. Remaining is on neon, but it starts the lamp and then it comes down. A bit reddish, that's why. But sodium is used in the street light because this is a lot more efficient, current-wise, electricity-wise. So you try to do the same experiment. You see some color, I have a color, but let's say you see a yellow-green two cloths in daytime on the tube light. In the evening, go below a sodium light. You have to know which is sodium light. You will have difficulty in that. Because now that all the wavelengths are not there, you are having only illumination with yellow color. So unless you are, but by birth you will know which are these colors, but suppose you didn't know, then this will be a problem. So that's why colors are very important, and all these estimates are based on the visible band V, which is shown here, and the rest is all. So blue side, of course, less sensitivity, and red side, and usually the detectors, which are CCDs, which is in your cell phone, are silicon devices. And silicon band gap, 1.2 electron volt. You see the wavelength cutoff, it is 1.1 micron, which is 11,000 angstrom. So typically 1000 nanometer. So infrared red side silicons has better detection. Blue side very poor. So they do some kind of coating to enhance it. Whereas photographic films, had a very poor sensitivity on this side, but in the blue side they were more sensitive. Okay, now let's move on. So this is again a similar thing. Blue star can have, the stars can be as hot as even 30,000, 50,000. We'll just soon see that. And this is our sun-like star, and red star like Betelgeuse or Aldebaran, which is Rohini. So this is the Planck's law. In frequency and wavelength, frequency is q, and wavelength is phi. And these are the usual constants. And remember, this nu is the frequency c by lambda. If you differentiate, that's why lambda square comes. And that's why it's 6 here as lambda. This is a basic thing people tend to forget, but this is the straightforward reason for that. And what are the cases? If this is the condition where nu is very, very large or lambda is very small, we have Wien's displacement law. The lower one is, the upper one is easy to remember, and we'll soon see this. There is a constant which can work. The other side is your white sky looks blue, Ranjan's law, lambda to the power 6 here. And of course, if we integrate the black body. Now remember, this is very important. These two infinities are sitting. This is all theoretical, ideal. In real life, there is no infinity. We will be measuring only from one lambda 1 to lambda 2. So you will get a total energy if you integrate this, and this is the Stephen-Boltzmann constant and T to the power 4. This has direct implication in astronomy. So at the bottom, I have done that. And for a star like Sun, which has a temperature 5700 degree Kelvin, this is 6 kilo. So Sun is a sphere. At each centimeter square, 6 kilowatts of energy are coming. That doesn't mean it will come all the way to us. Firstly, it is direction, all direction. But we are at one direction. So only the part which we are seeing will come to us. It will get absorbed in the atmosphere and so on. So there are a lot of processes. Ultimately, it is not 6 what you get per centimeter square on Earth. And this is per centimeter square, remember. You have a telescope which is catching that. And telescope has a diameter centimeter square. So you will only see a part of that. And then you can actually calculate what is the actual intensity of that star or the number of photons which are.
Sir?
Yes? Loud.
Yeah, just out of curiosity. The last slide. Or you showed this one.
This one?
No, the last slide. Yeah, no. Suns. Yeah. So you said that like we adapted to the peak. Like why not different sort of constant? Like,
Why not?
Why do you say that we adapted to it?
Okay, it's the nature because the human eye, sunlight was always there. Right? So when humans evolved, they could say everything illuminated by sunlight, not through a white light or not through LED or tube light. See? So naturally we are used to that. That's why our sensitivity is good in that. Okay, whereas the modern detectors like CCD are more sensitive on the right side, on this side. Photography films were on this side. But they were not natural, they were the actual detectors. I don't know whether I answered your question, but this is the humanity's evolvement to that environment. Suppose we were on Mars and we would have seen only red sky. Mars is supposed to have, probably we would have been sensitive in light. Okay, so I have come up to this. So Wien's displacement law, this is much easier to remember, lambda into T. This you remember the 3 minus 3 meter Kelvin. Remember this is meter. So use this, and this is where the astronomy starts flowing in. Star whose temperature is 5000 will look yellow because 5800 angstrom is a yellow color. Similarly, difference is Sun, roughly 0.5 micron and 6000. Next is Earth. This is important. Earth, the average temperature is about 27 degree Kelvin, let's say. So 27 degree centigrade. Not now it's too hot, but general average. So 300 degree Kelvin. You put in these numbers here. Earth is radiating its peak at 10 micron in the infrared. That's why if I have a satellite which is observing in 10 micron, if Earth comes in the field of view, it will saturate. So they will avoid Earth in that case. Then the last one is, of course, cosmic magnitude, where there will be many lectures. Again, sorry, I will not talk on that. But that is 3 degree Kelvin. And all this cosmology is 3 degrees Kelvin was after the universe formed. It was supposed to be uniform at 3 degrees, but there are micro fluctuations in that degree, which people work back to say how the universe was formed. Beyond that, I will not talk. But this 3 degree Kelvin is the most famous. All this WMAP or all the later satellites which are, but they are all talking of the variations in this mean 3 degree in different directions. So you see, it's all consequence of simple black body law. I will skip this because you can always see. So I also mentioned, just like as I said, there is something called real black body measurement, which is ideal. So it's called bolometric measurement. So there is something called bolometric flux, and just like the magnitudes, apparent bolometric flux, and this is related to this from the Stephan-Boltzmann law. You see the sigma T4 here. This is the distance of the star and so on. So you can actually find the luminosity. Now, why this slide I am showing, this word luminosity is very confusing, at least in observational astronomy. As we will see as we go along. This here luminosity means the total output of that object, in this case is a star. The luminosity in case of star is also defined how much is the absorption of the absorption line and called the luminosity of the spectra. So it becomes pretty confusing, and towards the end the instrument also has a luminosity. So it can become pretty confusing unless you get clarified. This is the first time you are enclosing luminosity here. So this is again a very similar relation. All this is the log scale and all that, apparent, and this is the absolute bolometric magnitude. So there is similar thing, bolometric correction is small m and visible. And why this is coming? This is the ideal, but actually your instrument, the bolometer is a general word, it's an instrument, which is not infinity to infinity, it's only measuring lambda 1 to lambda. So you have to correct for as if it was a real instrument. So this is that correction. Okay, now this is another important thing called color index. I have written in red and blue. Very hot objects will look, very hot will look blue, but usually, for example, this, all of you at least have experienced in a dark room. You might accidentally forget to switch off the heater or the pressing iron, it looks reddish. That is because it's not that high, black body works. But very hot things will look bluish. So the magnitude I already defined, B is 2.5 log of that flux in that band. So B minus V is called color index. Now this is negative for a hot star. The magnitudes between blue and red. And this will become very clear just now. At a cool star, it is positive. Because magnitude definition is that way. So effective temperature of the star, like sun, can be found from the Stephan-Boltzmann law, sigma T4, provided you can observe the energy in all radiation possible. But that's not ever possible. So rather, people do this. Check at 2 different colors. As soon as you do 2 colors, the black body radiation curve is locked. You can tell the temperature. More the bands, better. But at least you need 2 colors. So that's why the spectral sequence, the star is hot or cold, defines the type of spectra. So this is just a quick thing. Hot stars are O, B, A. These are the main stars. But there are other later ones. Hot will be O, B, A, F. Just to remember, people try to use this. But basically, there are 7 main spectral types. And this is the table. And a little bit time here. All stars are very blue, 50,000. See, it's a very hot star. So everything else has evaporated. So what remains is a very light gases, which are hydrogen and helium. So helium, then hydrogen, helium. And then it becomes, now the temperature is cooling down, 11, A-type star. The Sirius is actually a blue star, but it is somewhere here. So it's an A-type star and H, hydrogen is down. Now slowly you're cooling down the stars. Yellow, white color. Now calcium, weaker hydrogen lines are there. Now this is sun. Now the metallic lines are there, the heavier elements are there. And you keep going, this is a K-type star. So yellow star like Capella or Arcturus, if you know the stars by name, they look yellow. Of course, orange is like Betelgeuse or, no, these are red. Some stars are also orange, red and so on. So now you see heavier and heavier elements are there. And now we have come down to 3,000. Usually you won't call it as a star if it is below this temperature. Then it could be a hot Jupiter or something. There's a lot of argument on that definitions. This is what is called as a HR diagram or Sprung-Russell diagram. The beauty of this, you will see some more pictures of this. In one shot, you can divide the stars. So suppose you make thousands of stars their observation, and on the x-axis you measure the temperature by some method. On this side, the luminosity compared to sun. Sun is 1. So let's see. I can try to make it a little bigger probably. So you see, oops. I have to. Oops. No, it's not going. I have to make it. Yeah. So, okay, I will not try to make it big. So if you put them, there is a line here which is called the main sequence. So if you see thousands of stars or hundreds of stars, most of the stars are on this line. And it depends how they evolve. They become supergiant, they become giants, and this side they become very compact. So, for example, Procyon, Sirius is sitting here. These are bluer stars, this side, and this side are redder and redder stars. And this side is, of course, the temperature. And this O, blue star, B, A, F, and you can see the colors also. There are other ways, this is a bit crude, but this is another simpler way. Main sequence here, blue giants, supergiants, and then this side here, white dwarfs. So this basically talks about the evolution of stars, and somebody will cover, I will not, how the star lives evolve. It can be usually starting from the main sequence, or it can go depending on the way the star is evolving. It can be a compact or a joint. Now, this is the last point here, and I think I will not continue beyond this today. At the moment, there is something called 0 point, which I will not define right now, but this everybody knows. 1 watt is -7 ergs per second. So 1 photon is this many ergs. Now, I define vega, 0 magnitude. So if I put 0 here in that formula, if you remember, I get 1000 photons. Remember this unit here, centimeter square angstrom second. Centimeter square because it is radiating from the surface of that star in case vega, 0. And angstrom because you are talking in a particular band. Maybe 1 angstrom wide or 10 angstrom wide. And per second, you are observing every second. Okay. So now this light comes all the way, the 1000 photons from the star which has come out from one point of the star. You have a telescope of some size. So that size will cancel this. Then you are using a color band. We will discuss bands tomorrow. It will be 1000 angstroms typically. So the visible band is peaking at 5500 angstroms plus minus 500 angstroms. So this 1000 will cancel this. And if you observe for 1 second or 10 seconds, this will. So you will eventually have some photons coming to you. But this is assuming there is no scattering effect and all. So ultimately for a 0 magnitude star, you will hardly have a few photons coming out end of the day. Now that is after the detector which has an efficiency, it's not 100% and so. But imagine we talked about 23rd magnitude faintness. So even fainter, lesser the photons, you have to integrate for a longer time. But still you are able to do that. So imagine it's all because of the log scale, I think. So 0 magnitude star is only giving you a few photons, which you are able to detect. But if you go fainter or fainter, that number will be. So that is why it's a complicated compromise. You need to collect more photons. Bigger the telescope, more photons will come, so that problem will resolve. But you still have diffraction and all. And I have not yet talked about the photometry, which is just these big bands. When you do spectroscopy, per bin the number of photons are even less. So that is why, obviously, when you want to do a star, say Betelgeuse, which is a star, you want to do photometry, it is easy. But if you want to do spectroscopy, you are dividing the same number of photons into smaller bins. So per bin number of photons are reducing, so you will still have to collect more light. So this is a very interesting thing which we will see tomorrow. At the moment, I will stop here, and we can take the questions from both. And what I'm going to do is I will have to go back to Zoom to see if there is a question on the Zoom. see. Meanwhile, you can ask.
Let's use this mic, okay? If
Yeah.
anybody wants to ask questions.
Any question, don't hesitate. Anything? I'm not able to see the chat window here. Oh, maybe I. Yeah, the chat window is open, but I don't see any questions there. Because tomorrow I will be moving into photometry and how do you combine the instrument with the telescope and this kind of things. Why, some question is why the sun has different color. I don't know what is this question because the question itself is stupid. I explained it so many times. Each star has its own color depending on the temperature. It's a black body radiation, not ideal black body. The sun's temperature is about 6,000. That's why it looks that color. Other stars have different temperatures, so their colors will be different. And we have only talked the overall black body. We have not talked the real spectra of the star, which is not exactly an ideal black body. Because the stars have atmosphere, so each atmospheric species will have its own absorption feature. So we will see that tomorrow, but the overall spectra looks like a black body. That's why the stars are called as approximate black bodies. I think I answered that question on, but anybody else?
That's the brightness.
Louder again.
So does the brightness depend on the exposure time? Like how much?
Wait a minute, you are asking slightly involved question. So you are talking of the exposure of taking let's say the image of a star. Let's say you are observing Betelgeuse star. Now your question is whether the exposure time. So obviously exposure will be more, right?
So how do we determine?
So okay, it's a little involved question. Firstly, nowadays people don't use photographic film, but otherwise it was a different way to do. But now, for example, you observe a standard star. In this case, it could be Sirius, which is not really a standard star because it is huge, or Vega. And I told you the number of photons, how you can calculate. So in principle, but you don't even have to go to that level. With Sirius, you take an image, say 10-second image, you say it is saturating your CCD camera. I'm giving an example to the mobile system, but the professional CCDs are much more sensitive. In fact, the level from 0 to 16 bit is several levels there. So you usually would expose it to 80% because you don't want it to be exposed also, overexposed. At the same time, you don't want it to be low because the noise will dominate. So once you have done that, for a standard star, then you know the magnitude. If somebody else has measured, then you know the magnitude. So you know how much exposure time you can change. But basically, there is a formula which I will be covering. S to N, signal to noise, depends on square root of time. This is a very important thing because suppose I observe something for 10 seconds and 100 seconds. The signal is improving root of that. So 1 second exposure gives me 100 counts. 10 second will give me root of 10 is 3 point something. And this way you can keep improving. The good thing about your question is, in the night when telescopes are used, if it is a very faint object, you try to take longer exposure. But as soon as you take long exposure, the CCD, which is a detector, has cosmic rays filling it. So you can't take a single long one, because it will saturate because of cosmic rays, which you don't want. So you take several big of them, say 10 seconds, and co-add them. You match them and co-add them. The sky is moving, so you have to match them and co-add. And because of this root T, beauty of that root T is now you are building the signal. Root of time.
Does the noise also?
Does the
noise also contribute?
Noise is also. But noise, interestingly, is not going as root T. It's the signal which is. Right?
How do we segregate between the noise and the signal?
No. See, first of all, I can use the black wording for that. So what is happening is, This is a very crude example I am giving, but it is correct. So this is your noise, and there is a signal sitting here. Okay, this is a signal. Now, this is for 1 second. If I do a 10-second, this will increase slightly more, but this will increase that root of 10. This will keep on happening. The noise doesn't increase that much. It increases, but not. But the idea is you already want this to be detected in presence of this. That is the goal, which you are achieving because you are increasing the time more and more.
So for example, if you are observing an exoplanet, so suppose the host star has a stellar spot. So that means how do we, because the stellar spot is also revolving, right? So it will also give the same kind of.
So firstly, no, this is again a totally different subject, but in case of so firstly, when there are ways of finding the exoplanet, what you are describing is the shadow of that planet sitting coming on the surface of the star. So even now there is no way to actually image the surface of the star because the stars are almost a point of view. They are done by only few stars have been done by a very special technique. I will not describe that. But yes, essentially you are seeing the light curve. So if it is a dark spot on the star versus if it is a planet, that is the trick, because dark spot means it will be cooler. Sun has spots. Many stars have very large spots. So if that dark spot comes to you, the temperature which you are able to, the effect of that is as if the light is dimming versus a planet. So there are, I'm not an expert on this, but there are ways to distinguish that, whether it is a planet which has caused the dip or it is the spot of the star. Let's say your question, again the noise thing comes here, of course. So, but more importantly, when the object is going, the dips are very fast. So the observation has to be very fast. They are usually in seconds or milliseconds. So there are very special techniques to find it, which people have evolved. And of course, bigger the telescope, the advantage is signal. Anything? I have a question here. Multispectral image of sun by white color of sun are more prominent. Multispectral image of sun. You take multispectral, multiple region image of the sun will look different. So the question is not clear. Anyway, the person he or she can write to. I think there are no more questions. We'll continue at 11 tomorrow. Thank you. The next lecture is at 2:30, right?
I think 2:15, right?